Okay, so Physics Section 3.1, Part 3. The focus of today's lesson is going to be on energy transfers and energy transformations. So we're going to be looking at a couple of different systems, which are shown in the images there. So this is continuing on with forms of energy from last week, which you should kind of keep in mind as we are working through these. So concept number 3, energy can be transferred or transformed. This is page 206 in your notes. So the law of conservation of energy is similar to the conservation of mass from chemistry. So the law of conservation of energy states that energy can neither be created nor destroyed, but is transformed from one form of energy to another or transferred from one object to another. So transformed from one form of energy to another or transferred from one object to another. So even if the amount of energy in one object changes, it wasn't created out of nowhere, nor was it destroyed. It's just coming from somewhere else or going somewhere else. So take a moment to wrap your head around that idea. So total energy before must equal to total energy after. Consider the diagram below of a battery connected to a light bulb. First, draw in a second wire from the battery to the light bulb so that we have a full circuit. Otherwise, no energy will flow. So we've got our one wire already there. So we're going to connect a second wire. So the battery itself contains chemical potential energy, which is then converted. So sorry, not as it moves through the wire, but basically within the battery, it's converted from chemical potential energy to electrical potential energy. And that electrical potential energy, remember, is stored. So as it moves through the wires, it becomes electrical kinetic energy. Which, as it lights up the light bulb, is going to produce light, which is formally known as radiant energy. And also gives off, more so for older incandescent light bulbs, heat energy. Looking at the types of energy transformations and transfers that are occurring here, which I've kind of drawn out, I'm just going to re-talk you through this. So the battery on its own is chemical potential energy. If the battery is just sitting there and nothing is connected to it, it's all just stored chemical potential energy. That stored chemical potential energy will be converted into electrical potential energy and then to electrical kinetic energy as the charges start moving, and then it goes into our light bulb, which produces light, radiant energy, and also gives off some heat. So this is, as I said, especially true for incandescent old style light bulbs. CFL or LEDs are much more energy efficient, and so they give off less heat. They do still give a little bit off. Okay, so you can finish this off, which is on page, in reference to page 206. So the goal of the battery in our previous example is to create light energy. But as we noticed, not all of this energy gets converted to light. Some heat energy is produced as well. So did the energy from the battery get transferred to light energy, referring to all of it? And the answer to that is no. We had some heat energy, which is thermal. No energy transfer is 100% efficient. The above example of a battery and light bulb demonstrates this. Some of the energy from the battery was transformed into an unusable byproduct known as heat or thermal energy. This idea can be shown in the law of conservation of energy as well. So our law of conservation of energy, the total amount of energy before is equal to the total amount of energy after. But the difference is that not all of the energy is what we wanted. So in this case, we wanted light, we got some heat. So the difference between useful energy, which is light, radiant energy, versus what is not useful, heat, thermal energy. So when people started making the switch from incandescent to LED, it was done because the light bulbs are more energy efficient, so you can use less energy, therefore your energy bill will be lower. But in actuality, bills didn't drop as much as predicted, and why this was because old light bulbs were giving off heat. This heat was actually partially helping to heat people's homes. So when they switched to these new LED bulbs, people ended up cranking up their heat daily. So perhaps not the goal they were looking for, but these bulbs are still good and still last a lot longer than incandescent bulbs. So, and that keeps them out of the landfill, which is overall a good thing. Okay, so different types of systems. We previously discussed how systems and surroundings make up the universe. So we have different types of systems which dictate what happens with our energy and how much is lost. So sometimes the non-useful energy is considered lost. Notice the quotations. Different types of systems will determine if, in fact, the energy will leave the system or be transformed. So energy is lost, again in quotations, when it is not doing what it's supposed to do, i.e., energy that isn't converted to light is just given away and seen as not useful. In an open system, so we have three types of systems, there can be an exchange of both energy and matter with its surroundings. So for example, boiling a pot of potatoes without a lid, both heat and water vapor, which is matter, escape. So if you boil water and leave it boiling, it will eventually boil dry because the water is evaporating and it is taking heat with it. So i.e., if you were to think about putting your hand above the pot of boiling water, you could feel the heat coming off of it. And the matter in this case is the water vapor, which is the change of state that occurs when water is heated. In a closed system, energy can be exchanged, but no matter is exchanged with its surroundings. So, i.e., a boiling pot of potatoes with a lid, only heat escapes, the water vapor is trapped. So if you put a lid on your potatoes, it would have to be a super well-fitting lid, obviously, in order to kind of actually meet these conditions. So that seals everything in and prevents water vapor or steam from escaping. But if you have an amazing lid that keeps the water particles in, you'd still end up with heat escaping. So you could still feel the warmth coming off of the pot. The third system is what is known as a isolated system. So an isolated system cannot exchange energy or matter with its surroundings. So for example, if you could somehow theoretically boil a pot of potatoes in a sealed, insulated cooler, nothing escapes. So completely hypothetical because I'm not sure how you would manage to boil something in an insulated cooler, but in theory, no matter would be exchanged and no heat would be exchanged as well. So first let's look at our open system. So as we are boiling our water, without a lid, heat and water vapor are exchanged with the surroundings. So we have both energy, heat, and matter. Water vapor is leaving the system and will condense on things nearby in the surroundings, but not within it's not contained within the pot. So the explanation is that energy and matter are leaving the system. Okay, in our closed system, so we again have a pot, and again, excuse my awful drawings. So we've got some kind of lid on this, and then our handle. Okay, so because we have the lid on this, it's trapping any water vapor, but heat is still escaping. So heat leaves, which again is the thermal energy. But water, which is matter, stays. So energy leaves the system, but no matter leaves the system. Final example is our isolated system. So we have our pot of boiling water. It doesn't matter if the pot has a lid or not. If we have a pot with no lid, it is going to give off water vapor, but instead of leaving the pot in an open system, it's in an insulated container. So it's still within the system, it's still contained. So even though it's escaping the pot, it's still within the system. If this is a perfectly isolated system, we would have no energy or matter leaving the system. No heat would leave the insulated container, and no water vapor would either. So it would leave the pot, but it would condense within the insulated container itself. So although no heat is leaving, it won't cool down. Therefore, no water would actually condense. It would remain as water vapor, but it stays in the system. So why is it impossible to cook potatoes in an isolated system in real life? Insulated containers are not 100% perfect in our real world. Energy is still able to escape or enter. So energy can still get in and out. If you think about a cooler, so in your everyday life, so something that you might take camping or like to some kind of sport event, that sort of thing, it doesn't matter how great your cooler is, the ice will eventually still melt within it. So there are plenty of coolers that can keep ice in the form of ice for 24 hours, maybe a little bit longer, assuming you're not opening or closing it all the time, because as soon as you open or close it, it's no longer isolated. But eventually, at some point, enough heat energy gets in and that ice will melt. So we don't have an insulating container that has no energy transfer, at least not currently. So this is all just a theory. So it's a great idea, but isn't practical or realistic. So comparing energy transfer and transformations continued. Whenever a system releases energy, the surroundings absorb it. Conversely, whenever a system absorbs energy, the surroundings release it. So make sure that that first point that I just read matches your notes. The bolded surroundings may say systems in your notes, so just check and make sure that that, I think in particular, matches your notes. So make sure the wording is exactly the same to avoid any confusion. Okay, so the process can involve energy transfer, energy transformation, or both. When energy is transferred, it stays in the same form. It goes to a different place. When energy is transformed, the form of the energy changes, just like we saw with the light bulb. So consider a pool table. When one pool ball strikes another pool ball, the following happens. So mechanical kinetic energy from the moving ball, it then hits another ball, so that second ball starts to move, meaning it is getting mechanical kinetic. But in addition to that movement, you also hear a crack sound, which is sound energy being released. So there is also a little bit of heat generated from the friction, so thermal energy is also released. The mechanical kinetic energy is transferred to more mechanical kinetic energy of the second ball. The mechanical kinetic energy is transformed into sound and thermal energy. So this is why, because of that transformation part, your second ball will never travel as fast or as far as the original ball, because some of that mechanical kinetic has been transformed into heat and sound.
These are just a few examples of different scenarios of energy being transferred or transformed. And then maybe see if you can come up with your own examples. But take a minute, pause here so you can read these over. But this is officially the end of this video lesson.